All right, I think we're on the air. So today is March 12th, I believe. Yep. And again, thanks for being brave during the first hour or hour plus of this evening. And let's wrap up a few loose ends and then transition to our next major topic, which kind of meshes very much with some of the techniques we've been exploring over the last few weeks. By the way, welcome back from spring break. I hope you were able to relax a bit. I was not really on break. I went to a conference, the cs.luc.edu Computer Science Education Conference in Atlanta. This is a big annual conference in different cities each year, and it had almost 1,400 attendees, so including school teachers. So there's a wide spectrum, and there are also vendor exhibits. So it was a good experience. I like to go to this conference. Okay, so let me pull up the schedule for today. And there are a few things where I want to do a little bit of a recap. And the first one is, it has to do with recursion. And I just got an update notice, so I was just updating idea earlier today. Okay, so you might have gotten the same. And it's the usual two-step process. It tells you to update the IDE, and then you do that, and then it tells you to update the Scala plugin to get one that's consistent with the IDE. And there are still a couple of glitches, as we are about to see, but we'll just run this outside of the IDE. Okay. So here we go. So I expanded this a little bit. So here's the familiar, straightforward recursive definition of factorial. And here is an equivalent definition as a function value. This one's here really for pedagogical reasons, to make it more similar to the prefactorial, where we replaced the recursive call, the recursive call by a function that we pass in as a parameter, where we're kind of opening this recursive knot and exposing it as this extra parameter. So we had been going through this in some detail, right? And you were able to put this to work a little bit earlier today. Anyway, so this one is to match this one here mostly in terms of the typing, well, partially. Now the thing is, so these two, these first two are otherwise equivalent, and they also have this particular thing in common that we're about to look at. So can they be translated directly in a straightforward way into a while loop? That is one question I'm throwing out there. The other question is, what are the consequences of being or not being able to do that, of just kind of converting a recursive function into an iterative one using a while loop. Okay. And when we run this worksheet, let's do that on the command line. Okay. So here it is. Well, let's make it a tiny bit bigger. So that should be good. Factorial. The reason I'm going to run it is so we can see what's going on when we add that tracing. Okay. So here's the call trace for the factorial. So this is equivalent to the plain recursive one, where every time we make a call, when we look at the code again, every time we make that call, okay, the recursive call, that recursive call is embedded in a formula, in an expression. And what does that mean as far as finishing the computation of that expression goes? So let's say, suppose n, we're looking at the topmost version. Suppose n is 5. So we go into the else branch and we want to return 5 times factorial of 4. Can we return immediately? Why not? Pardon? Yeah. So why does it have to be on the stack for now? I mean, so we're making this call to fac of 4, right? And so we cannot compute. So it's simply, it's simply not ready yet until we make that call, and then it comes back, right? So that's basically right. So so let's say we're making this call 5 times factorial of 4, and we're waiting there. This is our last step before we can return that result. But before we can return that result, we need to make the recursive call, get that result, then we can evaluate our final expression and then return our result 5 times the actual result value of factorial of 4. That's right. So for every value of the factorial down to 0 in this case, we get basically a little record, a little object on the stack representing that pending call. So this little object is called an activation record. So for each invocation of a method or a function, there is going to be an activation record on the stack. So because we're not able to compute the result we're supposed to return until the result from the recursive call we're making comes back, this activation record for our invocation, which is for factorial of 5, stays there until the factorial of 4 invocation comes back. So once that comes back, we compute the result, return it, and then the activation record for our that first invocation goes away. But then for every recursive invocation, it's the same thing. So we get this stack growing until we reach the base case. And then once we reach the base case, the results get returned in the opposite order, and these activation records get popped off the stack again. All right. And again, the activation record is a little object representing this invocation or call that's still in progress. Okay. So when that's the case, and it really doesn't, this idea of the activation records is independent of recursion. The fact that we are using stack-based invocation of functions and methods allows recursion to happen. So in earlier versions of Fortran, such as Fortran 4, it didn't have that, so you could not actually express recursion directly. You would have had to build up this kind of stuff, kind of on top of what the language gives you. Whereas with languages that have this kind of stack discipline, recursion is directly supported in the language. So, that's been the case in Algol 60, in C, and so on. These early more algo-like languages, where algo-like would imply that recursion is directly supported. And of course, in Lisp, it's always been part of that. So in fact, it probably made its way into Algol because they saw that Lisp had it, and then they say, well, what can we take from this existing work? And then, oh, recursion, Fortran doesn't have it, so that looks like an interesting and powerful feature to put in here. Okay. So the challenge is now, well, when the recursive invocation is somehow buried in the computation of the result of the current invocation, the thing we cannot do is, we cannot say, okay, well, the very last thing we're doing is invoking or making that recursive call. It's really almost the last thing, but the very last thing here is the multiplication. So the multiplication of n times the result of the call, right, that is the very last step. And the second last step is getting back the result from the recursive call. So we would have a hard time converting this into a while loop, and you can try it, but if you try it, make sure that it's really equivalent in the sense that the value of n that it starts with, should be 5. And you'll have a hard time, So the question is there a way to express factorial in a slightly different way by making a minor change and then generalize this kind of technique to other similar situations where our time performance stays the same, but our space performance goes, well, let's analyze again from what to what, right? So let's look first briefly at time performance. Can anyone take a shot at the time performance of factorial in terms of n? The order of complexity in time. So is it, I'll give you some choices. Is it constant? Is it order n, where n is that argument? Is it order n log n, or is it order n squared, or something else? Who said n first? Can you justify a little bit? I think it's a...
Well, if every time you call it, you subtract -1 from n, it should just do the same thing.
That's exactly right, yep. Yeah. That's good. So you were saying n squared. Is there a reason you believe it should be n squared? I mean, if we assume that these other things like multiplication and comparison are constant.
The reason why I say n squared is when you hit like a very huge number, multiplication is n squared.
That's actually true. Yep. So that's actually a very good point to take into account. So you might have said, how did you get n squared? It makes no sense, right? But it does actually make a lot of sense. If you get into the range of numeric values where those values don't necessarily fit into a fixed size word anymore, and you can no longer assume that multiplication is a constant time operation. So this is actually a more advanced line of thinking, which is not really part of the way we're looking at it here, but this is true. So you would actually see this not when you use the ordinary int type, which is based on a fixed word size, right, like a 32-bit word typically, but if you, let's say, did this with big int, then this consideration would be very applicable here. Yeah, very good, thanks. So back to our assumptions here. So just regular int type and comparison and other operations such as multiplication and subtraction being all constant time. Okay, then order n is the right order of complexity here. So excellent. So in terms of time, there's really not much we can do. That's right. What about space? So as we just discussed, for each number for which we're recursively computing a partial result of this that gets multiplied into this factorial, we get an invocation. So we get n recursive calls, and we cannot really start coming back until we reach the base case, right? So all of the invocations starting with n equals 5, then 4, then 3, and so on, they're all there waiting to perform that last step. So once we hit the base case, n equals 0, then the second last one, so then we'll return 1 immediately, and then the second last one can say, okay, 1 times 1, then the third last one will say 2 times 1, and then they will all kind of come back, and eventually we're back to 5 times factorial of 4. That's our, the very last one before returning the final result, and then we're back, and the stack is back where it was when we called factorial of 5. So what is the space complexity? So in terms of n? Can you motivate that?
It's 1 plus 2 plus 2 plus and so on plus n, which is n.
Okay, be careful though. So
because in the first, like
right.
in the narrowest case, it's 1, right?
Right.
And then it goes up until like and then the biggest case is n. So you have
right.
to represent n in integers. Right?
But let's make the assumption though that each activation record is of the same size. So let's say, what does the activation record need to have? Well, we need to know what the argument value for that call is. Okay, so each is the same size, and there's one for 5, there's one for 4, and one for 3, and so on. So that sum that leads to the squares doesn't actually apply here. So there's really just for each, linearly. So for each value of n from the original argument down to 0, there's one activation record of the same size. Do you agree?
Okay.
Right? So that would mean the space complexity is also order n. When we write it like this, when we have this kind of recursion where the current call gets suspended, we make the recursive call, and then it comes back. This is when it's linearly recursive, because we're making just one recursive call. Okay? If you look at things like Fibonacci numbers, where you might have to make, like in a bad implementation of Fibonacci, where you make 2 recursive calls, and you have to wait for both of these to come back, then it could really get out of hand. And there's a whole, usually in complexity books, there's a section dedicated to that analysis, and it's quite sophisticated, and I remember vaguely it talked about an Ackermann function that grows really fast, even faster than factorial and so on. So when you do that, it gets out of hand, but no one in their right mind would, it's really just a theoretical study, because no one would actually write a Fibonacci in a way that it will ultimately behave like that. So you could write it in this way that it looks like the naive way, meaning Fibonacci of n equals Fibonacci of n minus 1 plus Fibonacci of n minus 2. And the reason it blows up like that is because there's all this multiplied work, the same work done multiple times, not just twice, but many times. So there could be an implementation that looks like that, but that uses invisible kind of memoization, meaning caching caching previous results so that those are just lookups, as opposed to redoing the work, and then it could be linear in time, okay? And it would be linear in space. All right, so that's basically the danger of having nonlinear recursion, where there are multiple recursive calls active at the same time, etc. But so here it's linear recursion. We have at most one recursive call, and the problem is, and this ties to the questions we were asking in conjunction with the problem in test 0 and the corresponding questions regarding project 1. Okay, so let's say you have very large input. Where does that input usually live? The choices are in main memory or not in main memory. So where would it be if it's not in main memory? Well, maybe on a hard drive. So usually a hard drive capacity is several, at least one, but usually 2 or more orders of magnitude larger than main memory. Even nowadays you have multiple gigabytes of main memory, 8 gigabytes here. You probably have some machines with more. But a typical hard drive is nowadays hundreds of gigabytes. Probably already, even small notebook hard drives are now in the half a terabyte and terabyte range. So that's where you get the 2 or more orders of magnitude difference, order of magnitude being a factor of 10. And that's why this issue is still important, even with multiple gigabytes of main memory. So you might have 100 times that in your data file, and you want to process the data. You cannot get around this. If the task is analyze the data, and this is what you have, huge data and not so huge main memory, you have to continue writing your algorithms in such a way that they can get by with limited main memory, relatively speaking. So that's why I was emphasizing so much this importance of not storing any of your input in main memory in something like Project 1, where you want to look at each input record once and never touch it again, okay? So this is kind of similar. Can we achieve something like this for factorial? And what we would want to do is, and I think I need to reveal that remainder of the code by doing this. So can we rewrite factorial in such a way that the last thing that happens, the very last thing, which in the original up there is a multiplication, with the return value, the recursive call, being a child of that multiplication, a sub-expression. Can we kind of twist it around so that the recursive call is the outermost thing, so that it really becomes the very last step, like here, okay? This is a crucial difference, all right? We'll see this shortly, okay? So the answer is yes, we can. I mean, you're seeing this here, but there's a little trick, and this is actually quite common. So the trick is we're introducing an argument called accumulator. This is just abbreviated for the accumulator, where we're accumulating we're successively accumulating a partial result. And we're writing the factorial with the accumulator in such a way that we'll say, well, if we reach the base case, we'll return what we've accumulated so far as our final result. Okay? Otherwise, if we're not at the base case, well, we'll recurse by invoking this function itself on n minus 1, and we're multiplying n into the accumulator we have so far. Okay? So now this, and I'm going to write it here. Now, you might say, oh, this is different from the original because now it takes two arguments. And when you look at examples like this in most languages, this version with the accumulator is an auxiliary function of an outer one that doesn't have the argument and just invokes, doesn't have the extra argument and invokes this auxiliary one with the same argument as the real one and sticks in the default starting value for the accumulator. And here we're taking advantage of a little bit of Scala syntax, which is a default value for arguments to the right of those arguments that cannot take default values. So that's what you're seeing here. So if I invoke it like this, without that second argument, it uses this default value as the value for that second argument. So this is equivalent to invoking fac_ac_5_1. Okay? And from there it takes its course. So what is that course? So we'll write a little imperative program here. So n is our starting value, for example, 5. Okay. The accumulator is 1. Right? That's our starting value for the accumulator. And then while n greater than 0, actually let's do this slightly differently. Let's use k here because n is what we get into the algorithm. It's an argument. So then basically that recursive call at the top level, the outermost and last thing, is just like performing these steps and then repeating. So we'll see this shortly. So here we'll say k is replaced with k minus 1, and the accumulator is replaced with, in fact, we have to do this in the right order. See? So that's the thing. When you modify things, you have to be very careful about the order. So we'll have to replace the accumulator first with accumulator times k. And then we can say k is replaced with k minus 1. Okay. And now you see how directly this if and the recursion translate to a while with the opposite of the condition in the if, right? This is the negation of that one. So we want to keep going as long as k is greater than 0. And then we do so the recursive call, this really means, because it's the outermost thing, it means do the same thing again but with these slightly modified values. So here we're modifying the values. We're updating them. Any questions so far? Yes?
Is that the same trick that the gentleman in the video at the beginning of the semester that we watched used? Was using the accumulator? You had us watch a video on Scala.
Yeah, I believe he probably did exactly this. That's right. So That's right. So I'm just re-emphasizing this because I think it's important to be aware of these choices that have an impact on performance. So I'm kind of just re-emphasizing this, but I think you did exactly this kind of equivalence. That's right. So I have these expanded comments here, so that we can compare notes. Basically, I'm sharing these thoughts with you. So the thing is, okay, so this now runs in constant space, right? Because it's a while loop, and we're not creating any more structures here. So I think everybody agrees that this while loop runs in constant space. And what a good compiler can do is when the compiler notices, oh, there's this opportunity here to transform this recursive invocation because it's in the last and outermost position, it sees the opportunity to transform it into iteration. Then we get this optimization from linear space, which might run out quickly if you're not careful, to constant space. So here you can keep going and keep going. You'll have numeric overflow before you run out of memory, right? So that's the thing. But that's because you do arithmetic operations. But if you did stuff like counting words and things like that, it'd be less likely. So that's just counting, adding as opposed to multiplying, where you might get a number overflow. Okay. So what Scala has, so in general, so the message is really, when you can, write your either write things as loops, but that really applies more to library implementers. And as I did mention, and I think I showed you the code, which you can browse very easily through the through the Scala API. The fold left is actually implemented as a while loop. Okay, so from a library implementer's point of view, yes, sure, just implement things very in this very optimized way, exploiting the possibility of these conversions. But it's also a little error prone, as I demonstrated by getting the order wrong here, right? So obviously you'll have to do testing and stuff. But recursive code, recursion allows you to keep things in a kind of declarative, immutable style, which tends to be less error prone. And therefore, you might want to keep things in this recursive style, but you might want to have a mechanism where the compiler will tell you if you messed it up, if it's not optimizable. And that's the purpose of this annotation. So this is an annotation that says, tell me if I didn't do the tail recursion right. So tail recursion is defined as the recursive calls in each branch in your code. The recursive call if there is a recursive call, the recursive call would have to be the last outermost thing that happens. So the original factorial without the accumulator is not tail recursive because the recursive call is not the root of the expression, even though it's the last thing that happens in the else branch. It's the only thing, therefore also the last, one of the last things, but it's not in the outermost position, so that means it's a child of the multiplication, meaning it really isn't the last thing. It is the second last thing, say.
because it's an operand of the itself operation.
Yeah, so you cannot return the result of the multiplication until you get that, and that causes this, basically this chain of nested recursive invocations. That's right. Whereas here, the way it works is like this. You can say, we're invoking fact act 5. So that creates the activation record on the stack for that. So here it is. And what are the key pieces of information? Well, the arguments. N equals 5 and accumulator equals 1. Then it does its computation. So it says, well, really all I do is the branching. So I go into here, and now I'm ready to return as soon as I get the result from this recursive call. And the tail recursion optimization means, well, why don't I return now by replacing my own activation record with the activation record of the recursive call. So that's how I keep the space constant. So as opposed to staying here, stacking one and possibly many more things on top of me, I say, let me go away and replace myself with the recursive call. That is tail recursion elimination. So that's that's what makes it equivalent to an actual loop. So here, what it does is it says, well, right now I'm an activation record representing factorial ACK of 5 and 1, and that is equivalent, because that's what this says declaratively, it's the same result as doing fact ACK of 4 and the ACK value of 5. So I'm replacing making some progress on uploading those pictures. I don't know if you've been on Facebook lately, but I'll get there. I'll also include these. So tail recursion elimination, or tail. It's not even only restricted to recursive tail calls. You can just call it tail call elimination. So replace current activation record often abbreviated as AR with new AR. So the example here is the original invocation, which is factorial accum 5.1. So you replace this with factorial ACK of 4.5. And then again you branch into the else. And guess what this becomes? Fact ACK of 3, and then here 5 times 4, right? And so on, right? So the result builds up, and that multiplication can be done immediately. I'm just writing it like this so you see the pattern. So in this way, you never have to have more than that one activation record on the stack. And it corresponds to a while loop. Yes?
I have a question.
Sure.
As for the normal recursion, I mean, aside that, is there any other disadvantage versus using the loop?
The only disadvantage is really the non-constant space. Right. That is, I would say, the one disadvantage. The advantages are that it's declarative, so you don't need mutable variables, so you might, you don't have these problems like getting the order of these things right and that sort of stuff. But really, yeah, the main disadvantage is the the extra space, and that's why when you do tail recursion, you have kind of the best of both. So you have the nice declarative thing, but you keep space constant, okay? But, you know, what's the price? Well, that extra accumulator, that makes things a little less obvious, right? So that's why, you know, you have to sort of convince yourself that this works like this, yep.
If I don't use that annotation, what will happen?
Okay, the purpose of the annotation is to get an error if you thought it was tail recursive, but it really isn't. Okay, so if what we would expect, you know, so it doesn't, the annotation doesn't have an effect if what you are annotating is in fact tail recursive and can be optimized by the compiler to a loop-like thing. So what we would expect is if we attach, and that's why I rewrote it in a straightforward way, you know, that's why I had to introduce that. So that now I can show this. I'll add it here, and we expect this to give us the error. That is the purpose of the annotation, okay? So now we'll rerun this, and pretty quick we will get this error. See here? So could not optimize at tailrec annotated method. It contains a recursive call not in tail position. So it does its job. So you can use this, and it will essentially confirm that you are, in fact, writing something tail recursively, and it will tell you if what you're doing is not really tail recursive.
So if you don't use that annotation, will it automatically?
When it can, it's supposed to optimize it automatically. That's right. This is really just to give you an extra assurance that you didn't mess it up.
So is this also supported in other programming languages like Java, C?
Oh, good question. That's a good question. You know, I think, well, in Java, in less recent versions of Java, I don't think the JVM supported this. So I don't even think the compilers did this. But I think in other languages, so in most functional languages that have been around, like Haskell, this is a very common thing, and it's one of the main optimizations that these compilers do. Okay, and so yes, and I think probably in C it would do it as well. In you know, these more mainstream languages. So you know, I'm not 100% sure. So I do encourage you to look it up, and maybe if you find otherwise, then report to the group. But it's really a very common optimization. That's why I think it's very important for us to be aware of it and of its existence and of its significance also. Okay. And if you look at the definitions, so fold left versus fold right. Okay. So we saw that fold left. We saw that fold left in Scala is implemented using a while loop. We saw that, right? So then fold right, on the other hand. Let me look at the definitions here in Haskell. Okay. So in Haskell, it's just called fold R. Okay. And you know, they have an auxiliary function here called go. It's no big deal. I'll put this at the top. But they have as a comment the straightforward implementation, okay, which is here. All right, so the second and third line. So fold right, over the empty list is just that zero value, the default value that you want when the list is empty, and fold right over a non-empty list, x concatenated or x const with x's, is f applied to x and recursively applying fold right to fx and the tail of the list x's. So what do we see here? What's the outermost thing of this expression that gets returned? Pardon?
Is it the fold R?
No, the fold R is the second argument to f. So it has, Haskell syntax is like this. You don't put parentheses. You say, so this means really f applied to x and then to the result of fold R. So what's the outermost thing? The last thing that happens here.
Should be F itself.
It's f, exactly. That's exactly right. So it's kind of like the multiplication in factorial, right? So, and the f could be a multiplication. If you do factorial over, if you do multiplication over a list of consecutive numbers, that's a kind of an elaborate way to get factorial. But so the thing is, the recursive call is not in tail position. So that's why, when you wondered maybe, okay, why does fold right run out of memory when you have large lists, or why does, let's say, why didn't Paul Phillips implement fold right using a while loop like they did for fold left? Well, simply because it's not tail recursive, you cannot do it. You simply cannot do it. So the only way to implement it using a while loop, I should say it more precisely, you cannot implement it using a while loop in such a way that it runs in constant space in a straightforward way. But you could implement it using a while loop, but you would simply replace you would simply replace implicit recursive calls with an explicit stack. So the space problem wouldn't go away. Okay. Then there's one other way to do it, but that is often deemed as a hidden cost. So you could reverse the list in constant space and then use fold left. So that would get rid of the problem, actually. But again, that's not built into the behavior of fold right because it could be considered a hidden cost that might not be necessary for many of the cases when you're not running out of memory. So that's that. Now the fold left, you can see immediately, where is fold left? It should be somewhere. So here's fold left. Okay. So here's a kind of informal definition of fold left, right? And more formally, so they're again using some auxiliary function, elgo, L for left. And here you can see that the recursive call is the outermost thing. So this is in tail call position. And you can, basically the compiler can optimize away the need to make a full-fledged new call. Instead, it just replaces the current activation record with a new one where the only thing that changes is instead of Z, you put FZX, and instead of the whole list, you put the tail of the list. So it's kind of like here or like here where we're replacing arguments, and then so we're calling ourselves just with a different set of arguments, but that's the last thing we're doing. So we can go away, and then the invocation with the new set of arguments takes our place. So we run in constant space. That's the tail call elimination optimization. Okay, so there you see how this works, why it can be done in fold left and why it cannot be done in fold right. And then you might wonder, if you're following some Haskell discussions and or you might have experimented with this yourself. So why does fold L still run out of memory? But that's a little more intricate, because what fold left does, it might not, because of the way Haskell is a lazy language, it might not immediately evaluate these things. So these might still pile up. Not the tail calls, but these invocations. And that's why there is a foldable prime, which is like fold left, but it evaluates that stuff immediately. So there should be a kind of SEQ thing here. So this says, basically this SEQ means do what's to the left first. So actually evaluate it and then make the tail call. So this really runs in constant space. So the fold L prime is equivalent to the fold left in Scala. So these are intricate nuances. You probably won't run into it for a while, but if you are doing anything in Haskell and you run into this issue, that's the reason. And it also helps, to see the relatively simple Haskell implementations that are quite straightforward, and then map them back to the Scala collections. All right. Again, so to summarize, I felt it was important for us to see this optimization, or the issue of space complexity and this possible optimization. This plays an important role when you're dealing with potentially large data sets. Okay. So there's a related recap, but I will make a brief digression because something I was just saying reminded me, namely the fold right. And basically, so project 2, most submissions were, as close to perfect as they can get, but really nobody fully understood this question, and I take part of the blame, obviously. So I think the choice of the name fold right was a little unfortunate, because it seemed to suggest to everybody immediately that the fold right was going to be applied to the children of a group. But what I meant here was the fold right, and it actually says it here, it's maybe just not as obvious or as clear as I was trying to make it. What I meant here is, and I'm just going into this briefly so that everybody can think think about this, and then maybe take another quick look at the grading comment that you might have gotten. So the idea is, so we have a shaped tree with some complexity, and we have the choice of using, for example, for computing the depth or anything, size, depth, any of these behaviors. The choice that we have been using is the catamorphism, in conjunction with the F algebra as the argument. So that is equivalent. So fold over a list is equivalent to that. Fold over a list is the special case of the catamorphism for list. That's why you get the 2 arguments. If you're looking at a nil node, you do the one thing. If you're looking at a non-nil node, you do the other thing. And in our examples, like expressions and shapes, we had many more branches. And instead of having for each possible branch a separate argument, like the list fold, we simply said, well, we're going to have a case distinction within a single argument, and that single argument is a particular F algebra in each case, right? So the branching is shoved back into that one argument. So that's why, for size is just one argument to the catamorphism with one branch for each kind of tree node we have. Does that make sense? Whereas size, if you do the size or length of a list, the F algebra is, if it's nil, then 0, else 1 more than the size we've already accumulated for our tail. Right? So it's really equivalent, but it's just expressed as 2 separate arguments for list because it's only 2, so it doesn't cause great inconvenience. But for anything with more than 2 branches, I would argue you're better off keeping the branching hidden in the algebra instead of opening the algebra and passing the branches of the algebra. All right, so that's that part. But what I really meant here is, what if I do a fold, kind of a non-catamorphism fold over a tree? So that's why I should have used any other name than fold right. I should have said, consider whatever a traverse or or even a for each or whatever over the shaped tree, where we would get a list of the nodes where we don't have the tree structure anymore. So will that work for size, for computing the size, for counting how many rectangles and ellipses there are?
Shouldn't work.
That will definitely work for size because it really does, we're just counting, right? It doesn't matter what context these shapes are in. So that's good. It will obviously not work for scale because scale is what you call an isomorphism. It preserves the structure. So scale is very similar to a map in the sense that the structure is fully preserved. The difference is, though, scale isn't exactly a map over the shape functor, but it's a structure-preserving transformation, so you could call that an isomorphism. But now, bounding box and depth. So let's start with depth first. So if we get just the nodes from the tree in some linear sequence, and we're looking at, for example, a group node, and we're supposed to figure out, depth values based on that. We really cannot, because the depth of any particular tree has a meaning in the context. Meaning, if this is a subtree of some other tree, then it's the depth of the maximum depth among those children, among those sibling subtrees, and then you add 1 for their parent, and then you pass that up. And that context structure gets lost when you flatten the tree. So you can no longer compute something like depth when that structure is gone. All right? What about bounding box? So, I should be able to, no matter in what order I see the ellipses and rectangles, I should say, anything I see that exceeds my current bounding box, I should be able to update the bounding box, right? Any dissenting opinions about bounding box? So when I look at a rectangle and it says, for example, 20, 40, okay. So width 20, height 40. Can I take those numbers at face value? I mean, does this mean it'll want to go only 40 into the height direction? Or does it depend on something else? Yes?
Depend on the location.
That's right. What you?
No, it wasn't.
Okay, excellent. So that's right. So even for bounding box, it requires that surrounding context to give meaning to the information in the subtree we're looking at. So you're losing that as well when you flatten the structure. That's right. And that's really what I was trying to get everybody to think about. So it's still good that we had a little discussion here. So the catamorphism properly it allows you to traverse the structure within the context. So that's the significance. So the answers here are: will it work for implementing size? Yes. Will it work for implementing bounding box? No. Or depth? No. Okay. Anyway, so otherwise, really good work. I'm impressed, and I'm sure it helped for the test also. So, all right. Let's see. So let me recap very briefly this list example here and show the tail recursion here. So there's a very similar thing. If you do a reverse, very similar to factorial. So you look at the reverse at the top. The last thing is appending the item at the end. So the recursive call is not in tail position. And then we've played around with a few things, right? Reverse as fold, that's fine. That's actually better because the fold left is tail recursive. It can be optimized. Reverse as fold right, again, not tail recursive because fold right isn't. But then we can also do things like reverse using an accumulator, so very similar, and all of a sudden the recursive call is in tail position. So it's a nice technique using these accumulators. So we're accumulating basically these items, and the way you want to think about it is, so you have a list 1, 2, 3, 4, 5. So you're taking the 1, the accumulator starts out empty. So you're taking the 1 off the head of the list, and you're adding it to the accumulator. And then in the next round, you're looking at a 2. You're adding that to the accumulator, so you're shifting them, and they appear in the accumulator in the reverse order. So you're adding them from head to tail, but what you add at the end is what was the tailmost element of the original. So that's why even though this looks like you're adding them just in the same order, they do ultimately appear in reverse order. And it's tail recursive. This could be a while loop, and it's good. So just wanted to show you, a different example in a slightly different domain here, right? So, all right. Couple of other things. Well, so I guess I gave you some of these on the test, right? So like this kind of stuff. The append can also be done nicely with an accumulator. All right. Now the natural numbers. Oh yeah. Okay. The primes example. We don't really have time to go into this in class, but I encourage everybody to take a look at this example. It's actually quite cute. So it's this functions on streams thing here. Very briefly. So it explores these successive filters to get the prime numbers, right? So you say, okay, the range. So I'm going to wrap it up here. So let's say the range of 2 to the largest number, let's say you want to find the prime numbers within that range. So we're always starting at 2, and then we're going up to the max within, for the range within which we want to find the primes. So initially you can say, well, let's filter out all the multiples of 2. That's the NO2, or no 2s, right? The no 3s, well, we take the no 2s and we filter out the multiples of 3. Then we'll take the no 5s, we'll take the no 3s, filter out the multiples of 5, which is really the head of no 3s. meaning that at each step, the head of the thing we have is the next prime. And then we take the tail and filter out the multiples. So that's basically the sieve of Eratosthenes. And this is the generalization of without multiples of. And then we could do this. So this is a recursive version without fold. Okay. And stream is similar to list, except it's lazy, so it computes the items as we try to access them. So therefore, streams can be infinite. So here, you can see that it works fine. The primes. Let's see. Yep. So this is a test method that we can then use so as not to repeat these things. So we can say test primes rec, and it works. Okay. Then we can express the primes as fold. And we'll say, well, we just at every step we'll have to get the next prime y, and then we want to get the rest with the filtered version where we filter out the multiples of that next prime. And then we apply this basically, let's see, we apply this over this range. So this is initially 2 to the max. So we're starting with a range of consecutive numbers from 2 to some max. And then we successively do the fold. The fold successively applies this step where we filter. And here's a little analysis why that's not optimal. And here, this is the missing discussion of the unfold or the anamorphism. So if you do it in a way where you're building it up or unfolding it from a generator, where the generator would tell you at any point, I have no more values for you, or I have another value for you, and here is the next value you should stick into the generator for the next step. Okay, so that drives the unfold. And here's the unfold right, which is up here. And you can have a general unfold for these recursive mu-based types. And that's what, this is the co-algebra deal. So this is the co-algebra. So whatever you stick into the unfold as the argument. Just like you stick an algebra into a catamorphism, or you stick the algebra into the cata, you stick the co-algebra into the ana, or the unfold. That gives you the anamorphism, and the terminology comes from catamorphism when you take a structure and you break it down and compute a result value. And an anamorphism is when you build up a structure using a generator, starting from a seed value. So you've seen those, and you've also seen isomorphisms, which are map-like, structure-preserving transformations. Anyway, so I just wanted to give you starting points here. There's a little more analysis, some final thoughts. And the natural numbers as an initial F algebra, that was basically on the test, right? Those flagpoles. The only thing that's in addition to them being natural numbers as these recursive things is the platforms. That was just a distractor, right? But you will see. So take a look at the natural numbers as initial F algebra, and it'll make sense. So you get those natural numbers if you take option as your underlying functor. So mu applied to option gives you, basically none, sum none, sum none. So each time there's a sum, that's one more added to the number. So it's basically a chain. And how does it relate to list? How does that kind of structure relate to a list structure? Structurally, basically the same, right? The only difference is list has in every node a place to stick an item value. But the skeletal structure is the same. So that's why when you look at the Scala mu examples, okay? When you look at the Scala mu examples, the only difference between nat based on option and mylist based on option is nat uses the mu that I provided, and the mylist uses the cofree that Scala Z provides, and the cofree is like the in or mu, but with an actual space for a value. Otherwise, they're the same, or rather, my mu is theirs, but with a unit value stuck to use up that space. So that space is taken by a meaningless unit value. But otherwise, it's exactly the same stuff. Anyway, so what I'd like everybody to do is, so we're basically here now. Next time I'll propagate this into next time, and we'll have presentations next time, etc. What I'd like everybody to do is raise any remaining questions you have about F-algebras, either in the Facebook group or at the beginning of next class. I want to give everybody an opportunity to get those questions addressed. I think it's useful for everybody to get their questions answered. Some of you came to my office hours today. That was excellent. And I addressed exactly some of these questions in detail. You can come in groups to the office hours. It's no problem. Or we can try to address these questions in the Facebook group as well. All right. So any questions now? Okay, very good. So see everybody next Wednesday at the latest. Let me stop the recording.